Look at a clock right now, or, just count to 15 in your head. I'll give you a second.
It's a really short amount of time.
Right. But in that tiny fleeting window of time, your body literally just manufactured 25 million brand new cells.
Which is just wild to wrap your head around.
It is. I mean, that is more new functioning biological parts than there are people living in the entire United States. And your body just generated them from scratch in 15 seconds. Welcome to the deep dive. Today, we are exploring the ultimate machine, which is you.
Yeah, as a human being created, it's really the most complex system on Earth.
Absolutely. And this specific exploration is presented by Dr. Risha, curating a path through some of the most fascinating biological science available today. And the whole goal is giving you actionable insights for your everyday life. Our mission today is to just completely remap how you view your own body.
Because, well, most of us were taught to think of ourselves as a collection of, isolated textbook chapters.
Right, like chapter 1 is the skeleton, chapter 2 is the heart, chapter 3 is the brain.
Which, is a convenient way to pass a middle school biology test, but it is a terrible way to understand human health.
Yeah.
The reality is that your body is a deeply interconnected, highly volatile, and dynamic ecosystem. Nothing happens in isolation. Every single heartbeat, every breath, even every time you scroll on your phone, you are initiating this massive multi-system collaboration that really defies simple categorization.
And to help us navigate this, Dr. Risha curated an incredible stack of sources for us to look at today.
Seriously, an amazing stack.
We're pulling Medical Portal Fast Facts from the Orthopedic Specialty Group and Live Science. We have these deep anatomical definitions from the experts at KenHub.
Right. And we're also looking at comprehensive educational guides from Mrs. Brunetto and Arvind Gupta.
Plus a phenomenal transcript from a National Geographic documentary. And this is my favorite part, an absolutely cutting-edge paper from the Arxiv repository that is literally detailing the mathematical modeling of whole-body human physiology.
Which is a heavy paper, but we'll break it down.
We will. So let's go back to that 25 million cells number. If we are regenerating our macroscopic and microscopic parts that rapidly, how do we even begin to map the human body? Like, if I look at a traditional medical chart, it feels like I am looking at two completely different languages at the same time.
You essentially are. I mean, to comprehend a machine that replaces its own parts at that speed, medical science relies on two simultaneous perspectives.
Okay, what are they?
You have regional anatomy, which is the map of where things physically sit, and systemic anatomy, which is the manual of what those things actually do.
Right.
The KenHub texts lay this out brilliantly. Think of regional anatomy as topographical. It divides the body into major physical territories, so the upper limbs, the lower limbs, the trunk, the thorax, the abdomen, the pelvis, and the head and neck.
So if we picture the human body like a massive, sprawling metropolis, regional anatomy is just learning the city by its neighborhoods. You need to know what is physically located in the downtown area.
Exactly. It is entirely about physical borders and proximity.
Yeah.
Take the thorax, for example, which is your chest region. It's physically bounded by the thoracic wall, so your ribs, and sealed at the bottom by the diaphragm muscle.
Like a literal physical container.
Right. And inside this specific neighborhood, you have an incredible packing job. You have the lungs, which are individually wrapped in specialized membranes called the pleura. And sandwiched right between those lungs is a space called the mediastinum.
That's where the heart is, right?
Yeah, that is exactly where the heart sits, locked inside its own protective sac, the pericardium.
Wow. And if you think that neighborhood is crowded, just travel south to the abdominopelvic cavity. According to KenHub, this region is lined by a membrane called the peritoneum, and it is basically the world's most chaotic but efficient storage unit. I mean, just the intestines alone snake around for 7.5 meters.
The physical mechanics of folding that much tissue into such a small cavity are astounding. To give you a visual from the text, 7.5 meters of intestines is the equivalent of taking 4 adult human beings, stacking them upright on top of each other, and then folding them up until they fit entirely inside your abdomen.
That is horrifying, but also amazing.
It really is. And that cavity also has to fit your liver, your gallbladder, your pancreas, your spleen, your kidneys, and your bladder.
So that is the regional map, the physical neighborhoods. But then KenHub introduces systemic anatomy, which basically throws the neighborhood map out the window.
It does. Systemic anatomy divides the body into 11 functional organ systems. You've got the integumentary, skeletal, muscular, nervous, cardiovascular, lymphatic, respiratory, digestive, urinary, endocrine, and reproductive systems.
Okay, so sticking with the city analogy, these systems are the utility grids. The power lines and the water pipes, they don't care where the downtown border ends, they snake through everything. The cardiovascular system has to push blood through the thorax, down through the abdomen, and all the way to the toes.
All right, they cross all the regional borders.
Here's where I get a little stuck, though. If the systemic grids, like the utility lines, are what actually keep the body running, aren't the regional boundaries kind of pointless? Like, why do medical students spend a whole year dissecting and agonizing over regional anatomy if it is the systems that do the actual work?
Because proximity creates shared vulnerability. A utility grid might run the whole city, but a water main break is a localized regional disaster.
Oh, I see where you're going.
Let's say a massive pipe bursts underground. That is a plumbing failure, a systemic issue. But the damage it causes depends entirely on its physical neighbors. It floods the subway tunnel below it, it shorts out the electrical grid next to it, and it collapses the road above it.
Wow, so you have three entirely different utility systems failing because of one regional proximity issue.
Precisely. Clinically, this is why regional mapping is critical. A sharp pain in your abdomen could be a localized issue with a specific organ, like an inflamed appendix in the digestive system. Or it could be a systemic failure crossing multiple regions, like a ruptured blood vessel from the cardiovascular system that is rapidly flooding the abdominopelvic cavity. If a surgeon doesn't know the exact regional map, they don't know what adjacent structures are in danger of collateral damage when a system fails.
Which brings us to this mind-bending Arkoff paper curated by Dr. Risha. This research takes the concept of systems and regions and translates them into pure physics and mathematics.
Yes, it is a phenomenal leap in how we conceptualize the human body.
They are looking at the body's entire physiological structure and breaking organs down into mathematical subcompartments to track the precise flow of blood and nutrients, right?
Exactly. The researchers don't just look at an organ, say, the liver, as a solid block of meat. They model it using fluid dynamics across three distinct subcompartments: the vascular space, the interstitial space, and the intracellular space.
Break that down for us. What do those spaces actually mean for the cells inside us?
Think of how a delivery truck navigates a city. The vascular space is the highway system, the massive network of blood vessels bringing oxygen and nutrients into the organ.
Okay, the highways.
But the blood itself doesn't physically touch your organ cells. The nutrients have to exit the highway and enter the interstitial space. This is the fluid-filled front lawn outside the cells.
Ah, the front lawn.
Finally, those nutrients have to physically cross the cell membrane to get inside the house, which is the intracellular space.
So the ArcSIF paper is using complex algebra and calculus to calculate the precise fractional flow. I saw they use variables like FO, FOY, and FOHOC to represent these exact volumes. They want to know exactly how much of a single substance moves from the highway across the lawn and into the house at any given millisecond.
And defining those precise fractional volumes isn't just an academic exercise. It is the foundation of modern pharmacological treatment.
Wait, really? How so?
Well, if you swallow a pill for a headache, that chemical has to navigate those three spaces. We need the math to tell us exactly how fast that specific chemical diffuses from the vascular highway, how much of it leaks into the interstitial lawn of your liver where we might not want it, versus how much actually penetrates the intracellular space of the targeted pain receptors in your head.
So it's regional and systemic anatomy fused together by mathematical simulation. That's incredible. By the way, if you were listening to this right now, I want to see if you can guess the answer to this before we say it. Think about the skeletal system for a second. What is a vital part of your skeletal system that is not actually considered a bone?
It's a tricky one.
I'll give you a bait to think about it. I would have never guessed teeth.
It surprises a lot of people. The Live Science text clarifies that teeth are absolutely part of the skeletal system. I mean, they are structural, calcified, and necessary for mechanical function.
But they aren't bones.
Biologically, no. Because of their unique tissue composition, primarily enamel and dentin, they are not categorized as bones.
And the bones themselves are fascinating, which brings us to the physical infrastructure of the body. If a ruptured vessel in our biological utility grid can flood a whole regional neighborhood, it makes sense that our most critical infrastructure needs to be heavily armored. Which brings me to the skeleton.
Right, the ultimate armor.
According to the Live Science and OSG sources, when we are born, we have around 300 individual bones. But as we grow, many of those bones fuse together, leaving a typical adult with a highly efficient 206 bones.
And the structural diversity among those 206 bones is an engineering marvel. You have the femur, the thigh bone, which is massive, dense, and built to bear the entire weight of your body in motion.
Yeah, that's a huge one.
But then, hidden deep inside your middle ear, you have the stapes, or the stirrup bone, which is smaller than a grain of rice and delicately vibrates to transmit sound waves.
Here's a statistic that forced me to completely rethink human anatomy. More than half of your entire skeletal framework, over 100 bones, are located in just 4 areas: your hands, your wrists, your feet, and your ankles.
Which tells a profound evolutionary story. Human beings did not evolve to be tanks. We don't have heavy, fused skeletal armor like an armadillo. We survive through unparalleled dexterity and mobility.
Oh, that makes sense.
Yeah, we need the ability to precisely manipulate complex tools, which requires dozens of tiny articulating bones in the hands. We needed to navigate uneven terrain and absorb massive shock impacts while walking upright, which requires a highly flexible, multi-jointed architectural arch in the foot.
But just because we aren't built like tanks doesn't mean the material itself isn't incredibly strong. The Orthopedic Specialty Group text points out something that almost sounds physically impossible. Pound for pound, human bone is stronger than steel.
It's incredible.
They note that a block of bone the size of a matchbox can support up to 18,000 pounds of weight. Let that sink in. 18,000 pounds on a piece of bone the size of your thumb? How is that physically possible?
Well, it comes down to microscopic architecture. If bone were solid, like a block of steel, it would be far too heavy for us to move.
Right, we'd be trapped.
Exactly. Instead, as the Arvind Gupta educational text outlines, bones are composite structures. The outer layer is compact bone, which is incredibly dense, but the inside is composed of spongy bone. It looks like a rigid honeycomb.
So it's mostly empty space?
Yes, but highly structured empty space. This structure, made of microscopic struts called trabeculae, distributes force perfectly. And within that spongy matrix, you have marrow, red marrow for manufacturing blood cells, and yellow marrow for storing fat.
So the bone is simultaneously lightweight, flexible enough to absorb impact without shattering, and capable of holding massive compressive loads.
That's the brilliance of it.
But a skeleton is just a scaffold. Without the muscular system, that skeleton is just a pile of incredibly strong matchbox-sized paperweights. The muscular system is the physical engine.
And it's a very diverse engine. We have 3 distinct types of muscle tissue: skeletal, smooth, and cardiac.
Skeletal muscles are the voluntary ones, right? Like the ones attached to your bones that you consciously control to walk or grab a cup of coffee.
Right. And smooth muscles are involuntary. They form the lining of your internal organs, like the walls of your stomach and your blood vessels, silently contracting to move food or regulate blood pressure without a single conscious thought.
And the third type?
Cardiac muscle. It's entirely unique to the heart, possessing an intrinsic rhythm that allows it to contract continuously every second of your life without ever succumbing to fatigue.
I want to focus on those skeletal muscles for a second, because the Arvind Gupta text outlines a strict biomechanical rule that tripped me up at first. The text states that muscles can only pull. They can never push.
That's a very hard rule.
But wait, I'm literally miming a push-up at my desk right now. When I do a push-up, I am actively pushing my body off the floor. When I open a heavy door, I am pushing it away from me. How on earth is that a pull?
It is one of the greatest illusions of human biomechanics. You have to look at how muscle tissue actually functions at a cellular level. A muscle fiber can only do 2 things. It can contract, which shortens its length and generates a pulling force, or it can relax back to its resting state. It has no biological mechanism to actively elongate itself and push a bone away.
So how do I push the door?
Through a brilliant system of biological levers and pulleys. Your skeletal muscles are attached to your bones by thick bands of tissue called tendons.
Okay, I'm following.
Think about your upper arm. You have the biceps muscle on the front and the triceps muscle on the back. When you want to bend your elbow, drawing your hand toward your face, your biceps muscle contracts. It pulls on the radius bone in your forearm, pivoting at the elbow joint. That is a clear, obvious pull.
Right, a classic bicep curl.
But when you want to push that heavy door open, your biceps relaxes. The pushing force actually comes from the triceps on the back of your arm.
Wait, how does the back of my arm push my hand forward?
Because the triceps tendon wraps around the back of your elbow joint and attaches to the ulna bone in your forearm. When the triceps muscle contracts, it pulls the back of the ulna toward your shoulder. Because of the way the elbow joint acts as a fulcrum, pulling the back of the bone causes the front of the arm to swing outward in an extending motion.
Oh, so when I push the door, my triceps is actually pulling backward on the lever of my elbow to swing my arm forward.
Precisely. Every single pushing motion you make is actually an opposing muscle group pulling a bone in the opposite direction across the joint's fulcrum.
That completely changes how I visualize movement. And speaking of incredible movement, Live Science points out a fun fact about our largest muscles. By sheer mass, it's the gluteus maximus, your buttocks. But by surface area, it's the latissimus dorsi, the massive V-shaped muscles in your back.
Both crucial for our survival.
Yeah, and the real fascination comes when we look at how this musculoskeletal system operates at peak performance. Because, let's be honest, humans often feel physically inferior in the animal kingdom. We don't have the anaerobic burst speed of a cheetah. We don't have the brute strength of a silverback gorilla.
No, we don't. But the OSG text highlights that early humans possessed one specific, devastating evolutionary superpower: persistence hunting. We are the undisputed champions of long-distance endurance running.
Explain the physiological cascade that makes us such good distance runners compared to a cheetah.
Well, cheetah relies on an explosive anaerobic metabolism. It burns through localized energy stores instantly to generate unmatched speed, but that creates massive amounts of metabolic waste and, crucially, massive amounts of internal heat.
Oh, heat.
Yes, a cheetah will overheat and face catastrophic organ failure in a matter of minutes if it doesn't stop. Human anatomy prioritizes a completely different metric: thermal regulation and biomechanical efficiency.
Yeah, our long legs give us incredible stride efficiency.
Yes, and our upright bipedal posture means that only the tops of our heads and shoulders are exposed to the direct blazing sun compared to a quadruped whose entire back is absorbing solar radiation.
That's a great point.
But our true secret weapon is our integumentary system, our skin. We are covered in millions of eccrine sweat glands. We can literally coat our bodies in water and rely on evaporative cooling to dump internal heat while we are in full motion. Most animals, like dogs or large cats, have to pant to shed heat. They cannot efficiently gallop and pant at the same time.
So early humans basically turned themselves into the ultimate horror movie monster. We would track a fast animal, like an antelope, during the absolute hottest part of the day. The antelope would sprint away at incredible speed, completely outrunning us.
But in doing so, its internal temperature would skyrocket. It would have to stop under a tree to pant and cool down.
And just as its heart rate begins to settle, the humans jog over the hill. We just kept a steady, moderate pace, sweating the entire time. We force the animal to sprint again before it has cooled down. We repeat this cycle for hours. Eventually, the animal literally collapses, dying of hypothermia and total exhaustion.
Our regional anatomy, the length of the legs, the structure of the glutes, the distribution of sweat glands combine to create an unstoppable systemic engine.
If you're listening, think about how your own muscles adapt over time. The biology here is ruthless but efficient. Over a period of seconds, a muscle changes from relaxed to contracted, an instant electrical and chemical spark. Over hours, it experiences intense fatigue as energy stores deplete and metabolic waste like lactic acid builds up. But over years,
It obeys the law of adaptation. If you subject a muscle to heavy loads, it experiences micro tears. The body responds to this systemic stress by signaling satellite cells to fuse with the muscle fibers, increasing their thickness and strength. That's a process called hypertrophy.
and if you don't use it,
If you sit on the couch and don't use the muscle, the body recognizes that maintaining that tissue is an unnecessary energy drain. It initiates atrophy, breaking down the muscle proteins to conserve calories. The musculoskeletal system is entirely use it or lose it.
so we have the structural scaffold of the bones, and we have the physical engine of the muscles. But an engine is useless without a pilot. We need to talk about the command centers, the nervous system and the endocrine system. According to the text, these two systems pilot the body using fundamentally different mechanisms.
One uses electricity, the other uses chemical warfare.
Let's start with electricity.
The nervous system is our high-speed electrical grid. It is divided into the central nervous system, which is the brain and the spinal cord, and the peripheral nervous system, which consists of the cranial and spinal nerves that branch out to literally every millimeter of your tissue.
The Ken Hupp text breaks down the brain itself into highly specialized regional zones. You have the cerebrum, the large, wrinkly mass taking up most of your skull. That is where you live. That is the seat of cognition, language, memory, and voluntary movement.
Right. But Kendall points out that the true unsung hero of survival is the brainstem, nestled right at the base of the skull.
Yeah, the brainstem doesn't care about your memories or your personality, does it?
Not at all. It governs the primal autonomic functions that keep the machine running: heart rate, respiration, swallowing, blood pressure. Canhub notes a sobering clinical reality. A patient can suffer massive trauma to the cerebrum, falling into a deep vegetative state where all conscious thought is gone. But if the brain stem remains intact, that patient will continue to breathe and their heart will continue to beat entirely automatically.
So the nervous system is the fast electrical network, but the endocrine system operates on a completely different timeline.
It does. It is a network of specific glands: the pituitary, the thyroid, the adrenal glands, the pancreas, the ovaries, and the testes.
And they don't use electricity.
No. Instead of shooting electricity down a nerve fiber, these glands manufacture chemical messengers called hormones and dump them directly into the bloodstream, where they circulate and bind to specific cellular receptors to regulate massive processes like metabolism, growth, and reproduction.
The integration of these two command centers is one of the most beautiful processes in human physiology. Think about a thermostat versus a light switch. The nervous system is the light switch. You touch a hot stove, in milliseconds, sensory receptors fire an electrical impulse up your arm into the spinal cord.
And the spinal cord processes the threat instantly and fires a motor impulse back down to your arm muscles. You yank your hand away before your cerebrum even consciously registers the sensation of pain. It is blindingly fast.
But if the nervous system is that fast and efficient, why did evolution bother keeping the slow chemical thermostat of the endocrine system?
Because you cannot sustain a lightning strike. Generating action potentials, those electrical nerve signals, requires a tremendous amount of cellular energy. It relies on actively pumping sodium and potassium ions across cell membranes.
So it's exhausting for the body.
Extremely. If the body needs to implement a sustained long-term physiological change, like adjusting your metabolic burn rate for the duration of a cold winter, or initiating the multi-year physical transformation of puberty, or even just regulating your sleep-wake cycle with melatonin, you cannot rely on firing billions of electrical impulses continuously. You would burn out the biological wiring.
So you turn the thermostat dial instead.
Exactly. You have a gland drop a hormone into the bloodstream. That chemical circulates quietly in the background, locking into cellular receptors and commanding those cells to change their behavior for hours, days, or months at a time, requiring very little ongoing energy from the command center.
Let's look at how the light switch and the thermostat collaborate during an absolute emergency. Canhub strongly advocates for learning applied anatomy through clinical case studies. So let's take a theoretical trauma scenario. A ruptured aorta.
That's a massive trauma.
Right, the aorta is the massive central artery exiting the top of the heart. If that vessel tears, you are experiencing catastrophic internal blood loss. What exactly happens in the command centers?
The response is instantaneous and multisystemic. The moment the vessel ruptures, specialized sensors called baroreceptors located in your major arteries detect a terrifying sudden plunge in blood pressure.
So the light switch flips?
The nervous system light switch flips. Electrical signals slam into the brainstem. The brainstem immediately engages the sympathetic nervous system, the classic fight-or-flight response. It fires electrical impulses down to the smooth muscles lining your peripheral blood vessels, ordering them to constrict tightly, attempting to squeeze the remaining blood volume upward to protect the brain and heart.
But the nervous system knows that an electrical zap isn't going to be enough to sustain the body through a prolonged trauma.
Right. So simultaneously, the nervous system fires a signal directly into the adrenal glands, which sit right on top of the kidneys. This is where the nervous system physically commands the endocrine system to take over.
It tags them in.
Exactly. The adrenal glands act as a chemical amplifier. They dump a massive payload of epinephrine and norepinephrine adrenaline straight into the vascular highway.
And what does that chemical flood actually do?
When those hormones wash over the heart tissue, they bind to beta receptors, forcing the cardiac muscle to contract with brutal pounding force and extreme speed to try and maintain pressure. When they wash over the lungs, they force the smooth muscles of the airways to dilate, pulling in maximum oxygen.
So the nervous system detected the crisis and sounded the initial alarm, but the endocrine system provides the sustained chemical warfare necessary to keep the organs fighting for survival.
Precisely. It's an incredible collaboration.
Which brings up a critical, actionable lifestyle tip derived from understanding this physiology. The fight or flight mechanism is a brilliant evolutionary adaptation for surviving acute life-or-death situations. A ruptured aorta, a tiger jumping out of the bushes. But modern human life is rarely threatened by tigers. We are threatened by chronic, low-level stress, traffic jams, endless emails, financial anxiety.
And your brainstem cannot distinguish between the psychological stress of a tax audit and the physical threat of a predator. The physiological response is identical.
That is so bad for us.
It's terrible. If you are constantly stressed, your autonomic nervous system remains chronically engaged in that sympathetic fight-or-flight state. It continuously commands your endocrine system to drip stress hormones like cortisol and adrenaline into your bloodstream.
Over time, that chemical thermostat being cranked too high becomes profoundly toxic.
It is devastating. Chronic cortisol exposure suppresses your immune system, raises your resting blood pressure to dangerous levels, disrupts your digestive tract, and alters how your body stores fat. The actionable takeaway here is that you must proactively manually override your command centers. You cannot just wait to feel relaxed.
So you have to trigger the parasympathetic nervous system, the rest and digest mode. How do you hack the system to do that?
Through the diaphragm. Deep, slow, controlled breathing physically expands the lower lungs and stimulates the vagus nerve.
Oh, the vagus nerve.
Yes. The vagus nerve sends an electrical signal back up to the brainstem, reporting that respiration is slow and steady. The brainstem interprets this data and concludes, well, the environment must be safe. We are not running. It then shuts down the adrenal alarm bells, allowing the cortisol levels to drop.
Wow. By consciously controlling your regional anatomy, your breathing, you actively regulate your systemic endocrine chemistry. That is incredible. Okay, let's transition from the command centers to the immense logistics network that keeps all of this running. We are diving into the supply chain and waste management, the cardiovascular, respiratory, digestive, and urinary systems.
We have to grasp the sheer ravenous demand of human tissue here.
Right, take the brain. The texts point out that the brain accounts for roughly 2% of a human's total body weight, but it demands 20% of the body's total oxygen and blood supply. It is an absolute energy sink.
And meeting the demand of 25 million new cells a second requires industrial-scale logistics. It starts with the respiratory system pulling raw oxygen from the atmosphere. Air travels down your trachea and branches into your lungs, which are packed with millions of microscopic, balloon-like sacs called alveoli.
The surface area math here is always staggering to me.
It's hard to visualize.
Yeah.
If you were to take every single alveolus in your lungs and lay their membranes out completely flat, they would cover the surface area of an entire tennis court.
A tennis court?
An entire tennis court of delicate, permeable tissue folded inside your chest, whose sole purpose is to allow oxygen molecules to diffuse across the membrane and into the blood, while simultaneously allowing carbon dioxide waste to diffuse out to be exhaled.
And once that oxygen crosses the membrane, it enters the cardiovascular system. The heart, which is a massive pump of pure cardiac muscle, is pushing roughly 5 liters of blood every single minute. It forces that oxygenated blood into a vascular network that Life Science notes is up to 100,000 miles long.
100,000 miles.
100,000 miles of biological tubing inside one single human being. That is enough to wrap around the Earth 3 separate times.
But oxygen is only half of the fuel equation. The cells also need raw building materials, which brings us to the digestive system. This is essentially a 30-foot-long disassembly line. You chew food, it travels down the esophagus and lands in the stomach, where a highly acidic environment and potent enzymes begin to denature the proteins and break down the physical structure of the meal.
But the stomach isn't really where you absorb your food.
No, the real magic happens in the small intestine. And just like the lungs need massive surface area to absorb oxygen, the small intestine needs massive surface area to absorb nutrients.
The engineering solution is brilliant. The inner wall of the small intestine isn't smooth like a pipe. It is densely folded, and those folds are covered in microscopic finger-like projections called villi.
And cells on the villi have their own microscopic projections called microvilli.
It is like a highly absorbent biological shag carpet. Those millions of tiny fibers slow down the digested food and provide maximum contact area, ensuring every single usable molecule of glucose, amino acid, and lipid is grabbed and pulled across the cellular membrane into the blood capillaries.
Right. And whatever the small intestine cannot absorb, mostly indigestible fiber, and water is pushed into the large intestine. The large intestine's primary job is waste management and water reclamation. It absorbs the excess water back into the body before the final waste is expelled.
And speaking of water, we have to talk about the urinary system, because the waste generated by cells isn't just digestive waste, it's cellular exhaust. The OSG text highlights that the human body is roughly 60 to 70% water.
The brain alone is 85% water.
Your kidneys are the ultimate filtration plants, constantly filtering the entirety of your blood volume, removing metabolic waste products like urea, and balancing your internal water and electrolyte levels.
To truly appreciate how this supply chain functions, let's go back to the mathematical fluid dynamics of the arcs of paper. Let's trace a single molecule of a nutrient through this messy organic system.
Okay, let's say you take a bite of an apple. The digestive system dismantles it. A molecule of sugar hits the small intestine, gets snagged by the villi, and crosses into the vascular highway of the capillaries. Where does it go? According to the ARCSIV schematic, it does not go straight to the heart.
No, it cannot. Blood exiting the gastrointestinal tract is full of raw nutrients, but it might also contain toxins or bacteria that slip through. So all the blood from the intestines converges into the portal vein, which routes it directly into the liver.
Ah, the liver.
The liver is the ultimate biological customs agent. It inspects the blood, metabolizes the toxins, stores excess glucose for later, and only then does it allow the clean processed blood to flow into the inferior vena cava and up to the heart.
The heart receives it, contracts, and blasts that sugar molecule out through the aorta, down through the branching arteries of the leg, all the way down into the microscopic capillary beds in your big toe. And that is where the ARCSIV mathematical model comes in.
Yes.
The sugar molecule has to exit the vascular highway, diffuse across the fluid of the interstitial space, and penetrate the cell membrane to give a muscle cell in your toe the energy to twitch.
And researchers need the algebraic equations, those FOV and FOI variables, to map the specific pressure gradients and fluid dynamics that force that molecule across those barriers.
I'm going to play devil's advocate for a second. We just described a highly squishy, chaotic, organic process, a shag carpet of intestines, a biological customs agent. Is it truly scientifically valid to reduce the sprawling messiness of human biology into rigid mathematical formulas?
We have no choice if we want to cure systemic diseases. Yes, human biology is messy on an individual level, but at scale, blood is a fluid, and fluid dynamics obey the laws of physics. Capillaries act as biological sieves, and diffusion follows predictable concentration gradients.
So the math cuts through the mess.
By modeling these fractional volumes with intense mathematics, a pharmaceutical scientist can sit at a computer and simulate exactly how a new chemotherapy compound will disperse through the interstitial space of a liver tumor versus how much will accidentally diffuse into healthy brain tissue. Mathematics cuts through the biological chaos and gives us predictive life-saving power.
That makes a lot of sense. And understanding this massive supply chain leads to two incredibly important, actionable lifestyle tips from our sources. First, hydration. Mrs. Brunetto's educational guide notes that roughly 60% of the water we consume leaves the body as urine.
Which is a huge turnover.
Yeah, I think people often view drinking water as just quenching a dry throat, but functionally, we drink water to physically wash the inside of our body. If you are dehydrated, your cardiovascular highway thickens, your blood pressure drops, and your kidneys cannot generate the fluid pressure necessary to flush the toxic cellular exhaust out of your system. You are essentially letting metabolic garbage pile up on the intracellular lawn.
And the second actionable tip is regarding diet and the microbiome. The Live Science text emphasizes that the large intestine is not just a trash compactor. It houses the gut microbiome, trillions of independent microorganisms, bacteria, and fungi.
Trillions.
These microbes don't just sit there. They actively ferment indigestible fibers, produce essential vitamins, and physically interact with your immune system to regulate inflammation.
You aren't just eating for yourself, you are feeding an entire ecosystem. If you eat a diet entirely devoid of fiber, you are starving your microbiome, which immediately impacts your systemic health.
Which perfectly transitions us into the final crucial aspect of our biology. Section 5, defense and continuation. The integumentary, lymphatic, and reproductive systems. If you have built this miraculous, highly functioning city with its electrical grids and immense supply chains, you absolutely must defend it from invaders.
The first line of defense is the integumentary system, your skin, your hair, your nails. It is the body's largest single organ, and it is the physical barrier against the outside world. It is the castle wall keeping the bacterial hordes out.
But physical walls will always eventually be breached. You get a paper cut, or you inhale an aerosolized virus. The moment a pathogen crosses the wall, the internal security force is activated. The lymphatic system.
The guards.
This is a vast secondary network of vessels and nodes that runs parallel to your blood vessels. Its job is to constantly vacuum up the excess interstitial fluid bathing your cells, filter it for foreign invaders, and deploy specialized white blood cells like lymphocytes and macrophages to destroy them.
And the communication networks here are incredible. The National Geographic transcript notes that the lymphatic system uses neural pathways, the nervous system's electrical grid, to transmit instant information about where a breach has occurred, allowing the lymphatic vessels to deploy healing agents and white blood cells directly to the site of the infection.
And here's a beautiful detail from the Arvind Gupta text that highlights how truly interconnected we are. We talked about organs belonging to multiple systems. Your white blood cells, the specialized assassins of the lymphatic and immune systems, where are they manufactured? They are born inside the red marrow of the long bones in your skeletal system. Your structural scaffolding is also your immunological weapons factory.
Wow. And I had a massive realization while reviewing the mechanics of the lymphatic system. The lymphatic system has thousands of miles of vessels carrying fluid all over the body, very similar to the cardiovascular system. But the cardiovascular system has the heart, right? A massive dedicated pump pushing 5 liters a minute.
Right.
I kept reading the text looking for the lymphatic pump, and I couldn't find one. If this fluid is so critical for our immune defense, how does it physically circulate without a hurt?
This is one of the most elegant examples of systemic dependence in the human body. The lymphatic system has no central pump. It is entirely reliant on the muscular system to circulate its fluid.
Wait, the muscles pump it?
Yes. The lymphatic vessels are physically woven through and around your skeletal muscles. They are equipped with tiny one-way valves. Every single time you take a step, every time you stretch your arms, every time your muscles contract, they physically squeeze the lymphatic vessels, forcing the lymph fluid upward through the valves, millimeter by millimeter, returning it to the circulatory system at the base of the neck.
Wait, think about the implications of that. If I just sit at my desk, unmoving, for 10 hours a day.
Your lymphatic fluid becomes incredibly stagnant. The circulation of your immune system's patrol cars slows to a crawl. This is fundamentally why sedentary lifestyles are so detrimental to systemic health. The muscular system is the literal engine that drives the lymphatic defense system. You have to move to heal.
That is mind-blowing. Let's think about a common experience. If you catch a cold or a throat infection, you often feel swollen, tender lumps under your jaw or in your armpits. Knowing what we know now about the lymphatic system, what is physically happening there.
Those lumps are your lymph nodes. Think of them as local police precincts stationed along the lymphatic highways. When a virus is detected in the tissue of your throat, the lymphatic fluid carries the viral particles to the nearest node.
And then the fight starts.
Exactly. The white blood cells stationed there immediately recognize the threat and begin to rapidly multiply, cloning themselves by the millions to fight the infection. The node physically swells and becomes tender because it is literally packed beyond capacity with immune cells engaging in microscopic chemical warfare against the virus.
And finally, standing above all of this incredible architecture and defense is the system that ensures the whole story actually continues, the reproductive system. The National Geographic transcript summarizes it perfectly. No matter how complex the nervous system is or how strong the skeletal system is, every single body system and every single human being began with the reproductive system.
The ovaries and the testes. And going back to the concept of multitasking, these are not just reproductive organs, they are highly potent endocrine glands.
Right, they release hormones.
They produce the hormones, estrogen, progesterone, testosterone, that not only govern the creation of the gametes required for fertilization, but physically sculpt the bone density, muscle mass, and even neurological pathways of the adult body. They allow the entire miraculous 11-system cycle to replicate and begin again. It is the ultimate biological act of continuation.
Let's pull all of these threads together. We started this deep dive with a stated mission to remap how you view your body. We wanted to destroy the textbook illusion of 11 isolated chapters operating in a vacuum.
And looking at the evidence, that illusion is shattered. You cannot separate the rigid strength of the skeletal system from the lever-pulling mechanics of the muscular system. You cannot separate the instantaneous electrical alarm of the nervous system from the sustained chemical flood of the endocrine system.
You cannot separate the digestive system's nutrient extraction from the cardiovascular system's mathematical delivery network, or the lymphatic system's immunological defense from the everyday mechanical movement of your muscles. The human body is a single, unimaginably complex superorganism. From the architecture of a matchbox-sized piece of bone supporting thousands of pounds, to the fluid dynamics of a single nutrient crossing into a cell, everything relies intimately on everything else.
Which brings us to a final, profound thought to leave you with. We spent time exploring the ArcSIF paper's mathematical modeling. Science is currently mapping the exact volumetric flow of every fluid and chemical across the vascular, interstitial, and intracellular spaces of all 11 systems.
Right, the absolute cutting edge of biophysics.
With the rapid acceleration of artificial intelligence and advanced computing, we are approaching a horizon where those mathematical equations can be fully rendered. We are nearing the ability to create a flawless, interactive digital twin of a human body, a mathematical simulation that accounts for the real-time integration of all 11 of your specific systems.
A completely digital mathematical you.
Yes. So the question we have to ask ourselves is this. If a doctor could load your specific biological data into a supercomputer and simulate a disease, or test an experimental chemotherapy drug, or model the precise systemic effects of a specific diet on your digital twin before it ever happens to your physical body, allowing you to see exactly how your unique interconnected systems will either fail or thrive 5, 10, or 20 years in the future, would you want to know your own biological destiny?
Wow, if the diagnostic medical chart of the future isn't a static X-ray of your broken bone, but a living mathematical simulation of your entire systemic future. Well, that entirely changes what it means to be a patient. Honestly, it changes what it means to be human. On that monumental note, we are going to wrap up this deep dive. Right now, wherever you are, I want you to just take a slow, deep breath. Feel the diaphragm muscle contract. Visualize the oxygen filling that tennis court-sized network of alveoli. Feel your vagus nerve signaling your brainstem that you are safe. Feel your heart pushing that oxygen into 100,000 miles of vessels, feeding the 25 million new cells your body just seamlessly created while I spoke this sentence. Take a moment to appreciate the relentless, staggering biological machinery that is keeping you alive at this exact second. From Dr. Risha and all of us here, thank you for taking this incredible plunge with us. Keep questioning, keep exploring the machine you live in,